Hello, and welcome to So You Think You Want to Take Organic Chemistry, the COVID edition. Coming to you live from my house because it's a global pandemic and that's where we spend all of our time now. My name is Sarah and I'll be your host for today. If you're taking Chemistry 1300 or 1310 and you're wondering about what organic chemistry is all about, we're going to spend some time today going through some of the techniques and experiments that you do in first year organic chemistry. Buckle your seatbelts, it's going to be a great time. Okay, so let's talk about the difference between washing and extraction. These are both techniques used in the lab for separating two substances that are both in the liquid phase. We'll get into the specifics of them a little bit later on when we overview all of the techniques that we use, but for now we're going to just learn how to decipher between the two, both of which use a separatory funnel, which is a piece of lab equipment that I've attempted to draw for you here, which basically the purpose of it is just so that you can pour liquid in through the top, and then using this little knob here, you can turn it and allow for small amounts of liquid to come out, so you have control over separating the two liquids. For an example, we're going to pretend that we have a homogeneous mixture of organic base and an organic neutral, and for reasons you'll understand in a little while, if you treat it with a strong acid like HCl, you're going to treat the solution there, pretending this is still a separatory funnel. After some inversion, you're going to be left with two separate layers based off of density. The aqueous layer, because water is quite dense, is going to be sitting on the bottom, the organic layer sitting on the top. We now have our organic neutral on the top and an organic base on the bottom. Using the knob that we have, we can then open it and allow for the solution on the bottom to drain out into a separate container, which allows us to then separate our organic neutral from our organic base. So what's basically happened here is we have washed the organic neutral or the organic layer from the aqueous layer on the bottom. And from that, we have extracted the aqueous layer. So that's basically the difference. Washing is something where you're going to remove something of interest or an impurity, and extraction is where you're removing something of interest. So we've extracted the bottom layer containing the organic base, and we have washed the organic neutral of the organic base. Now, the other thing that can happen here is we can further wash the organic neutral with something that we're not interested in keeping. So, for example, we could add some sodium chloride, throw it in here, and then it would give us another little aqueous layer to which we would drain it into a different collection vessel, and then we can just throw that away because we're not interested in keeping that solution. We just wanted to further purify or wash the organic layer. Okay, so let's try working through a problem. So say you were given a 3-gram sample of a homogeneous mixture of sucrose, benzophenone, and 2-naphthoic acid in equal parts. If these are all really small solid particles, how would you go about separating them from each other? So the first thing that I would do here would be to look up different solubilities of these molecules. Obviously from a reliable source, which can be found just online, I was able to find that both benzophenone and 2-naphthoic acid are very soluble in a solvent called diethyl ether, and conveniently sucrose is not soluble in the solvent at all. So a very quick way to remove sucrose would be to treat the entire solution with diethyl ether, which would leave us with a solution, an aqueous solution of benzophenone and 2-naphthoic acid dissolved in the diethyl ether, and we would be left with small solid particles of sucrose that did not dissolve in that solvent. From there, what I would do is I would put the entire solution into a suction filtration system, which is a technique that we use for separating solids from liquids in the lab that we'll get into in a little bit more detail later. But basically, it would just allow us to collect the solid sucrose in the top of the funnel and having drained the aqueous layer containing our other two components in the bottom. At this point, just to make sure that I have removed all of the benzophenone and 2-naphthoic acid, I would just take a little bit more of the cold solvent, the diethyl ether, and wash the funnel to just make sure that everything that is soluble in that solvent has drained through, and I am just isolating sucrose. So at that point, compound number 1 is done. I would then take the bottom layer containing the other two compounds and take a look at what the differences are between those two. So something that you might not notice right away, but if you're going to take organic chemistry, this is something that will become very apparent to you very quickly, is that the 2-naphthoic acid has a proton on it here that it is able to lose. So just in the way that we were able to separate an organic neutral from an organic base when we were using the washing and extraction example, you can also separate an organic neutral from an organic acid. The only difference here would be instead of treating it with an acid in order to protonate it, you treat it with a base in order to deprotonate it and therefore force it out of the solution. So what I would do is I would take the aqueous solution containing those two compounds and put them into a separatory funnel. I would then treat it with a strong base such as sodium hydroxide, which, like I said, would then deprotonate the 2-naphthoic acid, forcing it out of solution into the aqueous layer below the organic layer containing the benzophenone. At that point, I would just drain the aqueous layer containing the 2-naphthoic acid in its deprotonated form. I would take that and I would put it on some ice and I would reacidify it dropwise using some HCl. Just in order to allow the product to crash out of solution. And then I would treat it the same way that I did with the sucrose, where I have a solid in a liquid and put it through a suction filtration system, which allows me to isolate my solid product in the funnel. The last thing that I'm left with here is the organic layer containing the benzophenone. At that point, I would decant what's left in the separatory funnel. I would put it into a round bottom flask, and at this point, I would treat it with a drying agent. I think one that would work really well in this situation would be magnesium sulfate. And then once that has started to solidify, I would then attach the flask to a machine called a Rotovap, which essentially just allows you to connect the flask to this large device that then allows you to lower the flask down into a warm water bath, and then it turns it, and through temperature, increased temperature and pressure, it just allows the remaining solvent in solution to evaporate out, which leaves us with our solid product, at which point you can scrape out the solid that is contained in the round bottom flask, and you have separated all three solids. Okay, so the next thing that we're going to talk about is the organic synthesis experiment that we did in lab this year. Synthesis is basically when you're using different starting materials to synthesize a new product. In this case, we are using 2-naphthol and 1-iodobutane in order to synthesize 2-butoxynaphthalene. And basically how the experiment goes is we start with the 2-naphthol, which is a solid. Add a couple of sodium hydroxide pellets, which aid in the reaction, and then use 95% ethanol as our solvent. So we put those three items into a distillation flask, attach a condenser to the top, and put them on a hot plate. The other thing that we put in is just a little magnetic stir bead. So what it does, the hot plate actually has a stir function in it as well that you can turn on, which then reacts with the magnetic bead and forces it to turn, which just helps the reaction move forward. Once all of the solids dissolved, then we just remove the condenser for just a moment and put some 1-iodobutane into the distillation flask, reattach the condenser, and then the next step is to allow the reaction to what's called reflux, where you use the condenser in order to allow the evaporated liquids to rise up, hit the condenser, and come back down. Like what a condenser basically does is it has a water line coming in and a water line going out on the exterior wall of this glass tube. The purpose of it is so that this reaction, like many reactions, need to happen at a higher temperature than its boiling point. So instead of just losing all of the material that could just evaporate into thin air if we weren't using a condenser, what happens is the evaporated liquid then hits the walls of the condenser and then condenses, because it's a condenser, and then travels back into the distillation flask, so we don't lose that material. So refluxing, we allow that to happen for about an hour to an hour and a half in order to just allow the synthesis reaction to occur completely. At that point, the liquid that is left in the distillation flask, you can use that for a TLC plate, which is something we'll get to in a moment, but because it's in liquid form at this point, we would want to take it at that point and use it for the TLC plate. And then you do the workup. So a workup is basically just once all of the making and the breaking of the bonds is complete, you can isolate your final product. So how we did it in this experiment is we poured the solution in the distillation flask onto ice. And that does one of two things. First of all, it cools down the solution. And second of all, it increases the water content. Both of these things are unfavorable for our product in solution, which will cause the product to what's called crash out or precipitate out of solution. So you'll start to see pieces of solid that come out into the solution on ice. At that point, we use suction filtration, where you pour the entire solution. Once it has melted and we feel that all of the solid has exited, we pour it into a suction filtration system, which is another technique that we'll get to in a few moments, and isolate the solid product. At that point, you definitely want to weigh how much of the final product is resulting and note what its physical properties are. These can be compared with, not the weight, but the physical properties can be compared with literature values rather, in order to confirm its identity. And And then at that point, you can also do a melting point test. This 2-butoxynaphthalene should be melt at about a temperature of 31.5 to 32.5. We'll get into melting point and boiling point again in a little while, but that's another way that you can confirm the identity of the product. And you can do an IR spectroscopy, again, something we'll get into in more detail shortly. But in order to analyze this product, if we're looking at the TLC plate that came out from this reaction, the way that we can use this to check the purity of the final solution would be to compare it to the starting materials. So if you're looking at this here, you can see that if this is our final product, and this is where we have a combination of the two, and this is where we have our reactant, our starting materials. You can see that these little spots here are indicative of the starting materials, and on our product side we don't see those spots, so that's a pretty good sign that we have a pure product because the starting materials are no longer present. The other thing that you can look at is if we're looking at the IR spectroscopy, this is what it should look like for a pure solution of 2-butoxynaphthalene. We can see here that we've got our hydrocarbons over at this peak, which is consistent with what we'd be looking for. And then we've got our aromatic rings here, just about at around maybe 1600 wavelength. And you can compare that to what the IR would be for our starting materials, again, to look at the purity. So this confirms the identity. If we were to look at the IR for 2-naphthol, because you can see it's got this OH group here, we would see a very broad stroke over here, indicating that there is an alcohol present. So if there were still 2-naphthol present in our final product, we would see at least somewhat of that broad stroke on the IR. So that's basically how you can look at the analysis of the product in order to confirm the identity and purity. So now that we understand how the organic synthesis experiment works, let's take a look at the mechanism that's actually occurring. So if we're starting with one of our two starting materials of 2-naphthol, it is then going to be treated with the hydroxide from the sodium hydroxide that we use in the experiment. This being a very electron-dense molecule is going to attack this proton, which deprotonates this molecule. This hydrogen is then able to bond with the hydroxide, and it leaves as water. You're left with the deprotonated form of 2-naphthol in what's called the transition state, which is the high-energy state that allows us to get from reactants to products. And this oxygen now is more electron dense, or what is called nucleophilic, which gives it the ability to attack something that is electron rich, or electrophilic, or something that is a good leaving group. In this case, we have a good leaving group on the 1-iodobutane, which is our other starting material, which means that this is going to attack at that location, where the iodine will then leave because it's a leaving group, leaving us with the butane able to bond with the oxygen on the deprotonated form of 2-naphthol, which gives us our final product of 2-butoxynaphthalene. This is called a substitution mechanism because, as you can probably now see, we have essentially substituted the proton on 2-naphthol with the butane from 1-iodobutane to give us our final product of 2-butoxynaphthalene. So by now I'm sure you're thinking, oh my gosh, this is so fun and exciting. I'm definitely taking organic chemistry next year, but don't worry, there's still lots to go over. Let's take a look at the overview of the techniques that we use for purification and characterization of organic liquids and solids. For purifying organic liquids, we use distillation, and for solids, we use recrystallization. And then we have a variety of different techniques that we use for characterization of our product. So basically giving us the ability to confirm the identity and the purity of what we have either distilled or recrystallized. We have boiling point and gas chromatography that are used for liquids, melting point for solids, and then we use TLC plates or thin layer chromatography and infrared spectroscopy or IR for both solids and liquids. So let's take a look. So sometimes before you can purify an organic liquid or solid, you have to separate it from something else. We saw the example of using washing and extraction for two liquids, where you have a neutral and an acid or a base, which is then treated with an acid if you have a base, or a base if you have an acid, which then separates the liquid into two layers based on preferences in solubility and in differences in density of the two liquids, where you're then able to wash one layer and extract another. And for solids, you will use something called filtration. In the lab, we use two different types. We have gravity filtration, where you are just allowing gravity to do its work. You put a stemless funnel into a flask and a folded piece piece of filter paper into the funnel, pour the entire solution in, where the solids are going to be caught in the funnel and the liquids are going to drain through. You can also use suction filtration, which uses a specific type of flask that can attach to a vacuum that pulls air through. In this case, you're using what's called a Buchner funnel with a different little piece of filter paper. But again, you're putting the entire solution into the funnel, allowing the liquid to drain through, the solids to be collected in the funnel. But now you have the added benefit of the vacuum pulling the air through that just allows the solid that's collected in the funnel to dry a little bit further. And that's basically how we separate different substances in the lab. The methods that we use for purifying substances in the organic chemistry lab for solids is recrystallization, and like we said, for liquids, volatile liquids, we use distillation. Recrystallization, pretty much the most important step is choosing your solvent. So you're looking for a solvent that is going to not dissolve your solid at room temperature, but it is going to dissolve it when heated. So once you've picked your solvent, then you're going to dissolve your solid on a heat source, so that all of the solids dissolve, at which point some of the impurities that are not soluble in the solvent that you've chosen may remain in solution. So we can use gravity filtration in order to remove the solids and catch them in the filter paper and keep the liquid that has drained through. At that point, you want to cool down the solution slowly, and then once it's come down to room temperature, you're going to put it onto an ice bath. And at that point, because your solid is not soluble at room temperature, especially not when cooled, it will start to crash out of solution where the solid starts to precipitate out. At that point, once you've got your crystals forming, you can put it into a suction filtration system, again, like we just talked about, using the Buchner funnel, and your solid, which is your product of interest, which has now been purified, is collected in the Buchner funnel, where some of the other impurities that may have been soluble in your solvent will be collected in the flask. So with distillation, again, we are purifying a substance, but this time we're looking at a liquid. It's a little bit more of a simple process. It's just got a cooler setup. So basically, what you're doing in distillation is you're putting your liquid that is impure into the distillation flask and putting it on a heat source. You're connecting it to a condenser, which is that fun thing that we talked about in the reflux of the organic synthesis experiment, only this time we have it directed to collect into a separate vessel rather than going back into the flask. And we're going to attach a thermometer at the top and pay attention to the temperature. So you're going to really slowly heat up the solution, and then when the temperature plateaus, first of all, it's really important to note that that is going to be the boiling point range for your liquid of interest. And because it's the boiling point, at that point it is going to vaporize out of the solution and will be directed into the condenser, where it then recondenses into a liquid and can be collected in its pure form in the flask. So a fairly simple way to characterize liquids and solids is to look at their boiling point and melting point. If you're looking at liquids, you're going to be using boiling point, and for solids, you're using melting point. For both of these, there are things that you can observe throughout the experiment, like we just saw for boiling point in distillation. And for melting point, what we usually do is to take a small amount of the solid in small capillary tubes and put them in a machine called a Digimelt, which allows you to observe the melting point range. So the identity can be confirmed by comparing either of these to the literature values that you'd find on any reliable source online, and that can help you confirm that you are looking at what you think you're looking at. As well, you can look at the purity of your sample, because very pure substances have very narrow ranges of boiling points and melting points. So if you do see a very wide range, or if you see a depressed melting or boiling point, so it's a little bit lower than you would expect, you can probably assume that there is some sort of impurity in the sample. As well, we look at mixed melting points in lab, where you are looking at the melting point of a combination of two different substances, and what is generally observed here is that you see a melting point somewhere in the middle of those two literature values. So we're just going to take a few minutes to look at the last few techniques that we use for characterizing solids and liquids in the lab. This one's called IR spectroscopy, or infrared spectroscopy. It's basically just a machine that shines light through the sample. The one that we use has attenuated total resistance, so you have the ability to just put liquid or solid directly on the plate and let the machine shine light through. Different functional groups absorb light at different wave numbers, and that is how you're able to tell what you have in your sample. The more functional group that is present, the higher percent transmission it will be, or the stronger the peak it will be. Some very common ones that we see are alcohol, hydrocarbon. The CH3 groups are present in all organic molecules, and carbonyls, and anything past the 1500 wave number is not something that we're interested in. So we use this for identity because you can check to see if there are functional groups that you would expect to be there that actually are there, so you can confirm the identity of your product. And we can also use this to assess purity because if there's a functional group that you would not expect to be a part of your compound that does show up on your IR, it's a pretty good indication that you have some sort of impurity in your sample. We also use thin layer chromatography, where you are given a TLC plate covered with silica gel, which is called the stationary phase, and then you spot it with your product and something to compare it to on the spots shown. And then you put it into a jar with an eluent, which is called the mobile phase, and you allow the eluent to travel up the plate, where the eluent then competes with the product, and you're comparing product of interest in order to create a spot on the plate. You can use this to confirm identity because if you don't know the identity of something, but you think you might based on other pieces of evidence that you've gathered, you could compare it to what you think it is. And if you get the same spotting, it's a pretty good indication that that's what you are looking at. You can also use it for purity in the way that we saw before, where you can compare it to the starting materials and see if any of them are still present, or also just to see if you get a clean spot that shows that you have a pretty pure product, and if you have a spot that you weren't expecting, that you might have something else in solution. So last but not least, we have gas chromatography for liquids with a boiling point below 300 degrees Celsius. Just like in TLC, we have a stationary phase and a mobile phase, only here we're using a metal column and seeing how quickly the liquid travels through the column. That is called its retention time, and it is directly related to the identity of a substance, whereas the integration and the peak signal are related to the amount of the substance present. The gas chromatography produces this graph as seen here, which the data from this can then be used to produce a standard curve, and the line of best fit can be extrapolated from the standard curve in order to find concentrations of unknown substances. Thanks for watching this episode of So You Think You Want to Take Organic Chemistry. I hope you do.